Okay, hello algebras. Here's a conversation about graphing rational functions. And our calculators are going to be a big part of this conversation because our first step in almost everything we do is to go ahead and look at this value or this equation and pay attention to where our x's are. When we talk about having rational functions, what we're talking about is having an x in the denominator. So what happens with that x in the denominator is our larger values are going to give us a smaller number because a number like -3 is going to be in the denominator, making 1/3 a smaller value than 1/2. The interesting thing is when we have a fraction in the denominator, and you might want to go ahead and pull out your calculator to verify what happens in this scenario, but 1 divided by parentheses 1 divided by 2, those parentheses become such a big part of the conversation, and that's where we end up with actually a larger number. The math looks like this. If y is equal to, and we'll do -1/2, so 1 divided by -1/2 is the same as 1 times -2, because we're going to do what we call inverse operations. Multiplication and division are inverses of each other, just like -1/2 and -2 are inverses of each other. So the pattern that we see is here is going to be -2, and this is going to be -3. Dividing by 0 always gives us an undefined value. 1 divided by 1/3 is 3. This is 1, 1/2, and 1/3. We can verify those values on the table if we look at 1 divided by all the values of the whole real number system. Looking at the table, we can verify that, and then at the graph, this is where we start to see these curves, noticing that 0 is never a value, and that each of these values, when I talk about over 1, up 1, over -1, down 1, over 1/2 up 2, over 1/3 up 3, over 2 up 1/2, over 3 up 1/3. I can see what happens as this value gets closer and closer to each of my x and y axes. That's that asymptotic relationship that we talk about, where it allows us to see the fact that this graph is going to get closer and closer without ever touching that axis. So we wind up drawing it approaching, recognizing it's never going to touch, it's never going to cross. All right, a rational function is a function with a variable in the denominator. The graph of a rational function is called a hyperbola. And an asymptote, we're going to think of it as a boundary where that line snuggles up to but doesn't ever approach. So it's going to be a line that the graph approaches but never reaches. It doesn't touch it and it doesn't cross it. Rational functions have two asymptotes. Your vertical asymptote is always going to be written as an x equals 2 equation, and your horizontal asymptote is always going to be written as a y is equal to equation. As a real quick reminder, our vertical asymptotes we call vuxes because they're vertical lines with an undefined slope and an x-intercept and an x only in the equation. Our horizontal asymptotes have a 0 slope. That's what that O stands for. They only have y-intercepts and they only have y values in the equation and in the graph. Alright, so here's an example of a rational function, and notice I have an x in the numerator and denominator. So we still have that same kind of curved relationship, and we can take a look at this graph and see where those asymptotes happen. So I can see vertically that this graph never touches this line here of x is equal to -2. I can see that horizontally this graph approaches but doesn't ever cross or touch this line here at y is equal to +1. When we're talking about zeros, remember zeros and x-intercepts are the same thing. We can talk about where does this graph cross the axis. So this one's unique because it has 0, 0 as a x and y intercept. When we're talking about our end behavior, what happens as x approaches -infinity? So as all these x values approach -infinity, do you see how these y's come down here and they approach our asymptote at y is equal to 1? As our x approaches +infinity, the same thing happens from this direction. Y approaches +1. Now, our conversations about our domains and ranges are interesting. We're used to being able to put anything we want into this graph, but guess what? That doesn't happen. Oops, I forgot my U. That doesn't happen this time because of this asymptote. So my x values are everything from -infinity all the way, and I can look at every single x inner or x value is represented except for at that asymptote. So I want you to think about it as jumping over this asymptote and recognizing that the union of all the x's before it, hopping over it, and then all the x's after it are a possibility. The same thing is true with my range. I'm going to start at -infinity. I'm going to come up, but as I look at all these possible y values, they stop here at y is equal to 1. They hop over it, and then those y values continue on up here. All right. So we have to remember to put that numerator in parentheses and the denominator in parentheses. Your calculator knows the order of operations, and sometimes will make it harder for you. Zoom 6 is going to just be Zoom standard, which will readjust your axes to the default settings. If you have a TI-83, it's going to draw the vertical asymptote, but remember that one is not a part of the function. Okay, so let's take a look at some of these graphs. And again, I want you to get used to entering in your graphs to get a look at what they look like first. So 4 divided by parentheses x minus 2. When I hit graph or Zoom 6, I can take a look at and predict where that vertical asymptote and where that horizontal asymptote is. So what we're going to start talking about and figuring out is my horizontal asymptote is going to come from what we call a over b, or the fraction of the coefficients of the x's. Here you'll notice I don't have any x's, so this is going to be 0 over 1. That is going to give me a horizontal asymptote of y is equal to 0. Something to remember is if I have no x's in my numerator, then my horizontal asymptote is always going to be y is equal to 0, because that 0 axis is going to predict where that horizontal boundary line is going to be. So I can go ahead and I can draw that. Now my vertical asymptote, your vertical asymptote is always going to be where my denominator is equal to 0, because that represents that point where my graph is undefined. And the interesting thing is, when I enter that into the graphing calculator and I go to the table of values, wherever I see that error, that's going to be where that happens for us. So your vertical asymptote is always going to be where your denominator zeroes out. All right, your domain is going to be all those x values up to your asymptote. It's going to hop over the asymptote and then keep going. Your range is going to be the same thing. All those values up to the asymptote. It's going to hop over the asymptote and then it's going to keep going. Now when I'm looking at my zeros, I'm going to go ahead and say, hey, where does this graph cross the x-axis? Never. So there's not going to be any, because guess what? Y is equal to 0 is my asymptote. My y-intercept is always going to be, when I have an input of 0, what is my output? And that's one point I can go ahead and graph over 0 down to. All right, as x approaches negative and positive infinity, it's nice to be able to look at the graphs to see this happen, because this part of the graph snuggles up in here, and this part of the graph I can sketch, supposed to be hitting there, and put there. As my x values approaches infinity, that means my y values are getting closer to that asymptote from both directions. These ones from here and these ones from there. All right, moving on to the next one. My horizontal asymptote is going to be the fraction that comes from the coefficients of those x values. So my horizontal asymptote is going to be y is equal to negative 3/2. So that's negative 1.5. So I know that this dotted line here represents that horizontal boundary line. My vertical asymptote is going to be where my denominator is equal to 0. So I can go ahead and draw that in. My domain is going to be my x values from negative infinity up to my asymptote, hop over it, and continue on forever. My range is going to be from negative infinity up to my horizontal asymptote, hop over it, and continue on, what's a 3, forever. When I'm considering where my zeros are, when I go to my table of values, an input of 0 is going to give me an output of 2, and that's a perfect y-intercept for me. An input of 0 and an output of negative 2. But the next conversation is going to be about what x values give me an output of 0. That's going to be my x-intercepts. And my x-intercepts are going to happen when my numerator is equal to 0. So when I set my numerator equal to 0, at 1/3, an input value of 1/3, I get 0 out. Over 1/3 and up 0. Okay, so when I enter this equation into the graphing calculator, and I go ahead and I see the picture that it looks like, that makes sense with my asymptotes, but not my y-intercept And then I realized, oh, you know what I did? I used last graph's y-intercept. So instead I need to change it to negative 0.25. So this one is not going to be a point, but if I go over 0, down, and that makes more sense for where I drew my x-intercept, and that makes more sense because my graphs are going to be in these two opposite quadrants. Alright, so I can go ahead and sketch those graphs. They're going to sit inside of those boundary markers like this. Okay. As x approaches negative infinity, remember my output is going to approach that vertical or that horizontal asymptote. So y is going to approach negative 3/2 from this side and from this side. Is it a function? Yes, because it passes the vertical line test. Is it 1-to-1? Yes, because it passes my horizontal line test. Is it continuous? No, because I can't trace the whole graph without picking up my pencil. I have to make a jump from each of my two pieces. When I'm talking about my extrema, there's not going to be none, no hills and no valleys. It's never a time when it's constant. And if you look at it from left to right, it is always increasing. So from negative infinity to positive infinity, and it's never decreasing. There's no decreasing intervals. All right, little question about my asymptotes. So we'll go ahead and we'll recognize that my horizontal asymptote is going to be that fraction a over b of my x's. So my horizontal asymptote is y is equal to 2/3. Here it is. Now my vertical asymptote is going to be where this denominator is equal to 0. So your vertical asymptote, 3x minus 4, is equal to 0. 3x is equal to 4, and x is equal to 4/3. So this is going to be my vertical asymptote. All right, so that's 6-2. Keep watching if you need 6-3.